Hello everyone and welcome back to another episode of Mr. A's Math Podcast. In today's episode we're going to do another Common Core sample question review. This will hopefully help get you prepared for the upcoming Common Core Regents on Tuesday. And so we're going to work through some questions here. I will put the PDF in the video description below so you can download the PDF I'm working from. I strongly recommend you do that. That way you can follow right along. I've also tried to make the questions nice and big so you should be able to read them pretty well from the video. So let's get started. Here we have a question asking us to find the coordinates of a point on a directed line segment. Okay, so that just means it starts at K and goes to L. It has a direction. That partitions the segment into a ratio of 3 to 2. So the first thing I want to do is draw a picture for this. Anytime I can create a picture in geometry, that's a good strategy. Since K, -5, -4 is down in quadrant 3, and L, 5, 1 is up in quadrant 1, I'm going to need the whole 4 quadrants. So, whoops, looks like my pen is getting a little bit light there. I'll swap that out. So K, -5, 4, I could put that perhaps down here. Excuse me, -5, -4. And L, 5, 1, I'll put that perhaps over here. And so what they're asking me to do is break this line segment into the ratio 3 to 2. That means that I need to find some measurement where 3 times that number fits into that space and 2 times that number fits into that space. Well, the trick to dividing a line segment like this proportionally is that you first have to think about the change in x and the change in y. Right? This line segment is slanted, at least in this coordinate plane, which means you have to change your x and y coordinate to get from K to L. That means that if I want to divide it in the ratio 3 to 2, I have to also divide my x and y in the ratio 3 to 2. So if I could imagine there's some point on the side here that divides my y into the ratio 3 to 2, maybe that's about there, and there's some point that divides my x into the ratio 3 to 2, let's say that's about there, I can label these pieces 3x, 2x, and 3y, 2y to help me see what's going on, then this point right here, let's call it P, is the point that we're looking for. The point that if I go if I go 3 to 2 on my change in x, and I go 3 to 2 on my change in y, that's going to give me 3 to 2 on the original line segment. So to figure out that point is really quite straightforward. What you're going to need to do is think about what the total change in x is. Right, the delta x over here is from -5 up to +5, so that's a change of 10. And you're also going to want to think about what your delta y is. That's this side. Y starts at -4, goes up to +1, so the delta y is 5. So this yields 2 equations. First we have that 3x plus 2x equals 10, from this 3 and 2 being 10. And we also have 3y plus 2y equal to 5. That comes from this 3 and 2y being equal to 5. So over here we get y is equal to 5. On this side over here we get x is equal to 2. And now we just have to sub back in. So to get from K to P, I have to change my x coordinate by 3 x's. In other words, by 6. So I was at -5. The new coordinate for P is going to be -5 plus 6. All right, so that's where I started, plus the 3 times 2 to move me over. My new y coordinate for point P started at -4, but to that I'm going to have to change my y by 3y. Since, oh my gosh, I wrote y equals 5 over there, that's clearly not right. Y is only equal to 1. Right? 3 plus 2 is 5, so 5 equals 5, that's 1. So if I'm going to change my y by 3, that means 3 times 1, just 3. So my y is going to be -4 plus that 3. And here I have the coordinates of point P. -5 and 6 is 1, comma, -4 and 3, also 1. So notice my graph isn't perfectly to scale, but that's okay because this was just a sketch, right? When I'm drawing something freehand like this, it's a sketch, not necessarily to scale, because 1, 1 would be, a little bit higher over there. So that's all that means. 1, -1. Ooh, I'm really batting 1,000 here, aren't I? Sorry, -4 plus 3 is -1, so my sketch actually is pretty good. That kind of looks like 1, -1, doesn't it? I feel better. So here's one way that you can solve this problem, and this is the method you need to have in your pocket if these numbers don't work out nicely. They could give you a point where the coordinate you need to find is like 2.7, 3 and a third. So this will work no matter what the numbers are. However, there is another way to think about this that's a little bit simpler if you have nice numbers. Let me go back to that original point. Oh, excuse me, the original line segment, right? KL. Notice that the slope of KL is delta y over delta x, 5 over 10, which is to say 1/2, right? So that means if I start at point K and I go up 1 over 2, up 1 over 2, up 1 over 2, etc., I'll eventually get to L. So think about how many times that has to happen. If you go up 1 over 2, and then up 1 over 2, and then up 1 over 2, and then up 1 over 2, let me just move that over a little so you can see better. Up 1 over 2, let's see, 1, 2, 3, 4, 5, that's going to get me to point L. Take a minute to verify that, right? I went up 1, 2, 3, 4, 5 times, that's my delta y, and I went over 1, 2, 3, 4, 5 times, that's my delta x, 10. So, to get from K to L, I have to go up and over 5 times. Well, if I want a ratio of 3 to 2, that just means I'm going to go up and over 1, 2, 3 times. Right there. And that's going to be my point P. Right? Do you see what happened there? That is up and over 3 times. So that's going to be 3 times the length of this. Well, excuse me, that ratio will be 3 to 2 because this is only up and over twice. And we can double check this to make sure that we agree with our 1, negative 1. If I start at -5, 4, and I go up, 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 right? So I go up, 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 then my new y coordinate is going to be 4. Having a bad time with negatives today. 4 up 3 times. Well, that would be -1. My x coordinate started at 5. I went over 2, over 2, over 2. That means over 6 from -5. That would put me at 1. And there we get exactly the same point. So there's 2 ways to look at the same problem. It's nice to have this in your pocket. It's a little bit faster and easier, but you need to know how to do this in case the numbers don't work out nicely. So this next one's a very quick one. We have a regular pentagon. Remember that a regular pentagon, or any polygon, the regular part means all congruent angles, all congruent sides. So these are all the same, and these are all the same. In other words, when you see the word regular, you want to think symmetrical, right? Like a circle. So it's asking us if we rotated it clockwise around the center, so we're going to rotate in this direction, what's the minimum number of degrees it must be rotated to carry it onto itself? In other words, how far do you have to turn this shape until it looks exactly the same as when it started? As if you turned your back and then looked again, you wouldn't be able to tell if I changed it or not. The easiest way to think about this is to think about spokes on a wheel, right? So if you go ahead and connect these 5 vertices of the pentagon to the center, then you get what sort of looks like a rudimentary wagon wheel. So really this question is saying how far do you have to turn it until, say, that spoke ends up exactly where that one is. Because if A is where B is, the shape will look the same and you won't be able to tell. So it's really just asking you what's that angle right there. Now hopefully it's pretty clear that that angle is just 360 divided by 5. Why would that be? Well, all of these are the same angle. And of course if you go in a full circle, that's 360 degrees. So 360 divided by 5, which is 72 degrees, is going to bring A exactly to B. So the answer to this question is 72. And incidentally, if you take a look at my rap from last year, the 2014 rap, this is actually one of the principles behind the wheel stop scene in the very beginning if you take a look at the bridge. I'll put a link in the video that you can click on and take a look at that later. Now this question is an interesting one. It's telling us that we have an equation of a line, 2x plus y equals 1, and it says line M is the image of that line. Remember, image means after some transformation, and here it's after a dilation with a scale factor of 4, with respect to the origin. So that's just your normal scale factor and dilation. Well, your normal dilation. So here's what I want to first think about. How do I dilate a line? I mean, we don't really know how to do that, do we? We dilate points all the time, but we haven't dilated a line. So let's start with what this line actually looks like. Not solve for y, it's going to be a little bit hard to graph it. So the first thing I might want to do is come over here and just solve this for y. Take 2x away from both sides, that's not hard to do. You have -2x plus 1. So this is a line with a slope of -2 and a y-intercept of 1. So what does that line look like? Well, something like this, maybe if that's 1, and it'll kind of have a negative slope, fairly steep because it's -2. So here's the line we start off with, -2x plus 1. Now if I want to dilate this line with a scale factor of 4, well, I need to figure out what that means. So think, what can you dilate? What things do you know how to dilate? Points, right? Points are easy to dilate. You just multiply the x-coordinate and the y-coordinate by, in this case, 4. Well, isn't the line just made up of points? In fact, how many points do you need to create a line? More specifically, to define that line? Only 2, right? Once you establish 2 points, then there's only one line that connects them. So let's find 2 points on this line. The really easy one is going to be right here, 0, 1. That's the y-intercept, and it's right in the equation of the line. Probably the next easiest point for my money would be right here, right? Now that's not a y-intercept, that's an x-intercept. How do I figure out where that is? Well, if the equation is y equals negative 2x plus 1, if I'm on the x-axis, doesn't my y-coordinate have to be 0? So if you change the y to 0, then we can solve this equation for x and figure out what the x value is that makes y 0. So if we subtract 1 from both sides, we have negative 1 equals negative 2x. And dividing by negative 2, we find out that x is equal to 1 half. Okay? So there's 2 points on this line, 0, 1 and 1 half, 0. Well, now I'm going to simply apply my dilation. So if I dilate by a factor of 4, the point 0, 1, so I'll go over here at 0, 1, and I'm going to dilate by 4, and I'll do the same thing to 1 half, 0. 1 half, 0. So 0, 1 will end up at 0, 4. 1 half, 0 will end up at 1 half times 4, that's 4 halves, or 2, 0. So what's this new line look like? Well, there's 0, 1, 2, 3, 4. There's the point 0, 4. And if that's a half, I got to go to 2, 0. So maybe that's 1 there and about 2 there. Okay. And if I connect those with my ruler here, so you're going to notice that we get a line that looks pretty good and parallel to the original. Now that should make sense to you. When we dilate things, parallelism is retained. That's actually one of the concepts we use when we dilate and construct, right? If you've looked at any of my videos for constructing, say, a dilation of 5/3 or 3/5 or something, we need the fact that this parallelism is retained. So now all we need is the equation of this line. Well, we know that it's going to be y equals mx plus b, and we already know the y-intercept, don't we? 0, 4. So if that point up there is 0, 4, then my y-intercept is 4. So y equals something times x plus 4. Well, hold on a second. If it's parallel to the original line, then it's got to have the same slope, doesn't it? Since the original line had a slope of negative 2, so does this one. So y equals negative 2x plus 4 is the answer that we're looking for. Negative 2x plus 4. Make sure I get the right choice there. So that's the answer to this question. And again, what I want you to realize is that even though we don't know how to dilate a line, we know how to dilate points. And points are determined by lines. So simply choose a couple of points, dilate them respectively, and see where your new line ends up. So this question is asking us to take a look at a couple of circles. It says circle A is a radius of 3, circle B a radius of 5. Use transformations to explain why circles A and B are similar. Well, let's think about what similar means first of all. Similar fundamentally just means the same shape, but a different size, right? So it's not going to change the shape, the angles aren't going to change, and the ratios of corresponding sides are not going to change, but the size of the object might change. Well, here's where circles are fairly unique. They don't really have any angles, and they don't really have any ratios that change. Every circle has the same ratio of radius to circumference, right? That comes out in pi. Pi is the ratio of the circumference to the diameter of the circle, and they're all the same. So since there are no angles to worry about here, we can simply note that under a dilation of, now let's think, what would the scale factor have to be to take this triangle and turn it into this one? So in other words, let's call our scale factor k. There's some number that if I multiply 3 by k, it's going to equal 5. Does that make sense? I need to dilate this circle by a number so that when I multiply 3 by that number, I end up at 5. Well, that's a simple one-step equation, right? We can just divide both sides by 3, and we'll end up with k equals 5/3. So under a dilation of 5/3, what we get, it's a little bit of a sloppy 5, sorry about that, circle A will be dilated to a circle with radius equal to 5. And any two circles with the same radius are congruent. So A and B are similar. That's all you need to do there, right? This is the definition of similarity, that we can turn one shape into a congruent match for the other by a simple dilation. And in this case, we can do that with a dilation of 5/3. So this question is employing something called Cavaliers Principle. This is a new concept in the Common Core curriculum. It probably wasn't exposed to the students in geometry previous to this. And it sounds a little bit difficult if you think of the textbook definition, but essentially what it's saying is very simple. If you have two stacks of objects, or just two three-dimensional objects, and every time you take a slice, right, if you take a slice at ground level, and you take a slice a foot up, you take a slice 2 feet up, if every slice that you take has the same area, then those two objects are going to have the same volume as long as they both stop at the same height. Clearly, if one goes up much higher, then it's going to continue to accumulate more volume. So in this picture, we have a stack of, let's see, 23 quarters, right? So each one of these are quarters. And there are 23 quarters in this pile, and there are 23 quarters in this pile. So if you just think about common sense, clearly these are going to have the same volume. It doesn't matter if you stack quarters a little bit to the left or the right. You've still got 23 quarters worth of volume, however much volume a quarter takes up. And this is what Cavaliers Principle is stating. So what you'd want to say in order to use Cavaliers Principle is something along the lines of, since the cross-sectional area or slash, I'll say volume, because they're talking about quarters. So quarters have a volume, but we could think about even slicing those quarters thinner into area, right? Since the cross-sectional area of volume at each height is the same, and the height of the two objects is the same, namely 23 quarters, right? However high that is, then they are, or they have congruent or equal volumes. Right? So this is what Cavaliers' principle tells us. If we have the same cross-sectional areas or the same cross-sectional volumes at every height, then the two objects have to be the same volume if we're talking about three-dimensional objects, or a planar figure, two-dimensional, would have the same area. So in this picture we have a pair of triangles, and we can see that they've marked off that these two angles are congruent and these two angles are congruent. Now we should recognize right away that that means these two angles are also congruent, since the angles in a triangle must add up to 180. If these two add up to the same amount as these two, then these two have to be the same as well. So we in fact have a pair of triangles that are all the corresponding angles are congruent, so they're similar triangles. Remember, angle is enough to prove triangle similarity, right? So they gave us the similar triangles, but that means that the third angle has to be congruent as well. So what they're asking us to do is describe a sequence of similarity transformations that shows triangle XYZ is similar to triangle UVZ. Well, similarity transformations, there's only one of those, right? That's dilation. That changes the length, but it does not affect ratios or angle measures, okay? So this is going to be very simple to do. What we need to do is dilate by an amount that's going to make this length match with this length. So let's actually use the same technique we just used a moment ago. So this length is xz. So xz is going to be multiplied by some number k. Alright, so I'm going to put this in parentheses because remember that is just a length, it's a number, right? And I'm going to multiply it by k, my scale factor, and what does it have to become? Well, what does xz match up with in the other triangle? X is a one-tick angle, z is a double-tick angle. So this point, or excuse me, this segment xz has to match up with this segment zu. So that means xz times k, my scale factor, has to match up with zu. I'll put that in parentheses as well to avoid any confusion. So I can solve for k very simply by dividing both sides by xz again. So that means that my scale factor is going to be zu over xz. And if I scale by that, that will make this side match this side, which by definition is going to have to make all the sides match because these triangles are similar. All right? So let's see. So we can dilate triangle, let's call it XZY. I'll go 1, 2, 3, right? Triangle XZY by a scale factor of ZU over XZ, such that, all right, if you are unfamiliar with ST, that's such that means, you know, like with regard to this condition, such that XZ or X prime Z prime, let's say right after that dilation, is equal to now Z prime U prime. So now we've got that length the same, and these are going to be similar triangles because we can match that length. Now, in order to really drive the point home, what I'd like to do is actually get this triangle to line up right on top of that one so I can show that they're now congruent, that I've made the match. So let's think, if xz is going to go to x prime z prime, which is the same length as zu, then all we would need to do is sort of rotate that triangle around, right? If we take that and rotate it around to there so that x maps to u, well then y is going to map down to v. So let's go ahead and rotate triangle x prime z prime y prime, right? So this is the triangle after I do my dilation, clockwise through an angle equal to the measure of angle, right? So I'm going to rotate the triangle clockwise this direction through an angle equal to, well, what's the angle I need to rotate through? If I want to rotate x prime onto u, and z is going to be the center of rotation, that means I need to rotate through this angle, right? X, z, u, although x prime, z, u. So this is the angle that I'm going to rotate through. So through measure of angle x prime, z, u. Now that will match up x prime and u prime, right? So this will map x prime to u prime, and it will also map y prime to v. Oh, sorry, that's not u prime, that's just a u. U hasn't changed, right? Also map y, so y got extended to y prime, and now we're going to rotate around, and it's going to put y right on top of v. And y prime to v. So now we've got a sequence of transformations. Let me just bump that up a little bit. We've got a sequence of transformations, a dilation and a rotation that are going to map this triangle directly on top of that one. And so now we know that they're similar triangles because we can make this one exactly the same as this by just dilating and then proving that they're congruent by rotating around. So this question is asking us to explain, be careful about that word, that means you have to really think about what you're saying, why cos of x is equal to the sine of 90 minus x. Cosine, I should say. I'm being a little sloppy in my calculus bad habits there. Cosine of x equals sine of 90 minus x. For any x such that, remember we just talked about that such that in the last question, oftentimes we'll abbreviate that as t in mathematics, 0 is less than x less than 90. In other words, x has to be between 0 and 90, so it's not going to be an obtuse angle, or a right angle for that matter. So wait a second, cosine of x equals sine of 90 minus x. That means that, well, x and 90 minus x, those are complements, aren't they? Think about it. Pick any number you want from 0 to 90, and then take 90 minus that number. Those add up to 90, sort of by definition, right? X plus 90 minus x equals 90. So those are complementary angles, which means they're angles that could fit in the same right triangle. So a little picture will help illustrate what I'm talking about. Let's say you have a right triangle, and we'll call this angle A, and we'll call this angle B. So clearly A and B are complementary. That means that we can rewrite this as cos A equals sine B, right? These are equivalent statements as long as I'm working within this triangle, because A and B are complementary, so it fulfills that, and cosine of the one is the sine of the other. Well, let's think about that. Cosine of A, well, that would be the adjacent side. I'll write adjacent to A, right, over the hypotenuse. But hold on a second. The sine of B is going to be the opposite side. I'll write opposite to B over the hypotenuse. So you can see that the cos of A is, in fact, A, let's call that C, AC over the hypotenuse AB. And the sine of B is also opposite, AC again, over the hypotenuse AB. So here we have AC over AB, and so that's the reason. It's because x and 90 minus x are angles in the same right triangle. And the opposite side of 90 minus x is the adjacent side to x. The mathematician in me is just wanting to stipulate here, x and 90 minus x are angles in the same right triangle only because 0 is less than x less than 90, right? So for example, 300 and that was a bad choice. 300 and negative 210 fit this bill, right? 90 minus 300 is negative 210. So that clearly wouldn't fit in one triangle because a negative angle doesn't make any sense. But if x is from 0 to 90, then that's going to work. And that's a good way to explain what's going on here. So it looks like we have a proof in this question here. They're giving us some information. The first thing I always like to do is mark up the information they give me, put it in my picture. This way I'm done with the words and I can just focus on my picture. LA is congruent to DN, so I got those right there. CA congruent to CN. Okay, so let's see. CA is this piece here, is congruent to CN. All right. And you might want to make an extra note to yourself that it's just that part. So for me, that's okay because I know that I won't mark a segment if it goes past a vertex like that. But so like I know that that's AC when I mark it. But make sure that you mark that in a way that you understand it's AC and not DC. So AC congruent to CN, and angle DAC, excuse me, line DAC, that guy is perpendicular line LCN. Okay, well that is going to tell me that I have what kind of angles? Right angles, right? Perpendicular lines form right angles, so those are both right angles. Let me go ahead and number them in case I need to talk about them in the proof at some point. And what are they asking us to prove? Well, no big surprise, that those two triangles are congruent. So let's think about how we could do that. I'm going to do this in sort of a flow style proof. On the Regents, we don't have to be quite as formal, so it's nice to just kind of sketch things out in a paragraph style. So let's see. We'll start with this piece right here. If DAC is congruent perpendicular to LCN, so since DAC perpendicular to LCN, angle 1 and angle 2 are right angles. And let's see, do I need to say that they're congruent? I actually don't, because I'm looking at this pair of triangles and I'm thinking about what kind of triangle congruence I'm going to have. So if it's side angle side, or angle side angle, or angle angle side, then I'm going to need to say that these angles are congruent so I can use them in that type of proof. But looking at this, I don't see side angle side or angle side angle. What I see is side side angle, right? Side side angle. Now remember, angle side side, and yes, I'm not making a mistake there, that doesn't work in general, but it does in a right triangle. We just don't call it angle side side to avoid confusion. Do you remember what we call it? Hype leg. Right? Hype leg triangle congruence. So if I have angle side side, I want to look for, do I have a right triangle? And in fact, I do have a right triangle. So I'm going to be able to set this up. So let's see. Perpendicular lines give me right angles, right? So 1 and 2 are right angles. And angles 1 and 2, triangle. Let's see. If I call this LAC, triangle LAC, and triangle, so LAC, that would be DNC, are right triangles. Right? Now this is important, right? Perpendicular lines give me right angles, and right angles give me right triangles. I need this because I cannot use hype-leg triangle congruence if I don't have right triangles. They're the only kind with hypotenuses. So it's very important that you state you have right triangles. Now let's see, what else can we say? We've got a pair of right triangles here. They told us that these sides were congruent, and they told us that those sides are congruent. Well, let's see, LA is congruent to DN, which are the hypotenuses. And we also know that CA is congruent to CN, which are a pair of legs. Right? So here I've got my hype, I've got my leg in a pair of right triangles. Great. That means that triangle, LAC, is congruent to triangle DNC by hype, leg, triangle congruence. Right? Same hypotenuses, same legs, in a pair of right triangles, that's congruent triangles. And once they're congruent, well actually that's all we had to prove. I was thinking we might need to do a CPCTC step or something. So like a good question would have been, prove that say angle D is congruent to angle L. Right? So once you have the triangles congruent, then you could use CPCTC, corresponding parts of congruent triangles are congruent, to get any pair of angles or sides that you needed. However, it looks like we're done. That's all they wanted us to prove. So we can go ahead and put a proof box there. and move on to the next question. So this question is a rather involved trig question. It's going to take a little bit of work to get done, and in my attempt to make the text larger so you can read it on the video, I'm a little short on workspace here, so I hope you'll bear with me. I'm going to have to shift this around a little bit as we go. This first part is really just describing the picture. Lighthouse, coastline, lighthouse is 112 feet above the water, the front of the canoe is 1.5 feet above the water, so all of that is in the picture. I don't really need any of it. So let's go ahead and scroll that up so we can get to the stuff that we need. So let's see. At 5 o'clock, the observer in the lighthouse measured the angle of depression to the front of the canoe to be 6 degrees. So that's here. Now, that's going to form a triangle. That's going to allow me to figure out distances. So before I go any further, I'm going to draw that triangle. Right? So this is down to the canoe. Now, I don't want to deal with this 1.5 feet, so I'm just going to take it over here, right? If there's 1.5 feet over there, then how much is above the height, or how tall is the lighthouse compared to the front of the canoe? 112 minus 1.5, right? So that's 110.5. Hopefully that makes sense to you. And we have an angle of depression. Be careful here. An angle of depression is measured from the horizontal down, right? So that's where that 6 goes, not at the top. Very common mistake. So by alternate interior angles, however, I can get that 6 into my triangle by bringing it down like that. So hopefully that makes sense. 5 minutes later, the observer measured and saw the angle of depression to the front of the canoe had increased by 49 degrees. Okay? Determine a state to the nearest foot the average speed the canoe is traveling. So that's a second triangle that I need. So I'm going to draw, again, a second triangle here. This is still 110.5, and that's still a right angle. Now, let's think about what this angle of depression is. Right? So the angle of depression now is this whole thing, right? 49 plus 6. That's a 55-degree angle of depression. And again, by alternate interior angles, that's going to bring that 55 right down into my triangle there. Okay. So hopefully you can see those two pictures and that's making sense. I'll put a double tick just because I don't want to insinuate that it's congruent to that guy. So what are they asking us to do anyway? I'm really just decoding the problem at this point. Determine and state to the nearest foot per minute the average speed at which the canoe traveled towards the lighthouse. So what we want to know is between here and here, how fast was this canoe going on average? Well, speed, they're telling you right here, is feet per minute. So my answer is going to be in feet per minute. I know the minutes, it was 5, right? So the speed is just going to be the number of feet, right, divided by 5 minutes. I need to know how far they went in that 5 minutes so I can turn it into a foot per minute speed. Well, that means I need to know two things. I need to know what the distance was from the lighthouse to the canoe in the first one, and then I need to know what the distance was from the lighthouse to the canoe in the second situation. So these are two relatively straightforward, hopefully easy trig equations for you to set up and solve. We have the opposite side, 110.5, and we have looking for the adjacent side, x in this case, y in this case, so that's going to be a tangent, opposite over adjacent. So let's see, I'm going to set these equations up in this little space I have right over here. So we have the tangent of 6 equal to 110.5 over x. That comes from this left triangle. And we also have the tangent of 55 equal to 110.5 over y coming from that right-hand triangle. A little bit of algebra and rearranging is going to give me x equal to 110.5 over tan 6. This is just by cross-multiplying and then dividing by tan 6. And the same thing over here, I'm going to get y is equal to 110.5 over the tan of 55. Now it's time to go to my calculator, right? X is going to be an approximate answer here. Same thing for y. So I'll grab my handy-dandy TI-84. I'm going to go ahead and make sure that I hit the mode button and am in degrees, right? So if you're like me and do calculus and geometry back and forth, you got to be very careful you're in degrees. I am. So I can just go ahead and type in 110.5 divided by, whoops, I turned it off. 110.5 divided by the tan of 6. And that'll give me my x, which is approximately 1051.33. Now I'm going to show you a little trick here. I'm going to hit store, that's this button here, hopefully you can see that on the camera. If I hit store, and I can actually hit the x button, store it as x. Now my calculator is going to hang on to that number. If I type x, it has it. So I'm going to use that in a moment to figure out my speed. We'll do the same thing with y. So y is 110.5 divided by the tan of 55. And I get my y, so about 77 0.373. But I'm going to go ahead and store that as well, store. But I can't hit X because I already stored something as X. So I'll put that in Y instead. The way I get Y is if you look on top of your 1 key, you get a little blue Y there. So I'll hit alpha, then 1, that gives me Y, enter. So now for my speed, what I need to do is take the difference between those, right? I need to know what is Y minus X. So I can just ask my calculator to do Y minus X, enter, and oops, I got negative 973. That's kind of weird. What happened there? I went in the wrong direction, didn't I? Right, Y was the smaller number, X is the bigger one. Now it's just going to be the wrong sign, but just to illustrate the point, let's go ahead and do X minus Y, and we got 973.96. Now that's a pretty fast, I'm a little bit nervous about those numbers, I have to say, because let's see, well, 6 degrees, but then 49, so I mean, it moved a lot, so maybe someone didn't really think about this too much. We got about 970, really close to 4, right? So about 974 feet, because they wanted feet per minute, so we'll round to the nearest foot, which is equal to, now what we do is divide by 5, so 974 divided by 5, 194.8, that'll get us to 195 feet per minute, which is riotously fast. I'm really quite nervous that I've made a mistake here. Let me just take a look back through everything. This first triangle, we got 6 going down, so 110.5, the angle of depression is 6, and the angle of depression increased by 49, so that's 55, and let's see, Y, I'm definitely, make sure I'm in the right mode here, degree, yep, and I'm just going to double check my math, 110.5 divided by tan 6, that's right, and 110.5 divided by tan 55, I wonder if I had tan 5 or something? No, that is the right answer. That is a staggeringly fast amount of speed, I think, for a rowboat. I don't know. I guess it's per minute. I guess you go 200 feet in a minute. Maybe I'm thinking per second. So actually, I guess that's not so bad. So there's our answer there, 195 feet per minute. And that's the average speed at which the canoe traveled towards the lighthouse. In another 2 years, when you take calculus, you could work on the instantaneous rate of speed. But that's a story for another time. All right, we have a circle here and a whole lot of information, so we're going to start to decode. Diagram below, circle O, I can see that, diameter AB, radii OC and OD, so all of this I can see. The length of AB is 12, I can see that. The measure of COD is 20 degrees, COD is 20 degrees. I personally am very unhappy with the way they labeled that picture. I'm going to cross that out, and I'm going to go ahead and put a 20 degrees much closer up to that angle, and I'm going to mark it. Because to me, I don't know if that's the angle or the arc, that's very confusing. I suppose it's a central angle, so the arc is also 20 degrees, but let's not go down that road just now. So what we're asking to do is, if AC is congruent to BD, so let's go ahead and mark that in the picture right away as well, right? AC is congruent to BD. Find the area of sector BOD in terms of pi. All right, so hold on a second. That means we're looking for this piece of the circle, right? A sector is like a pizza pie slice out of a circle. Well, the first thing I want to know is how much of the circle that is, right? Because it's a percentage of the whole thing. So a diameter cuts a circle in half, so that's half the circle, this is the other half. If this is 20 degrees, well, let's think about it like this. If we have a 20, oh, a little bump over there. If I have a 20 degree angle there, and these two angles are the same, well, these all three add up to 180, right? So 2x plus 20 has to equal 180, which means 2x is 160 and x is 80. Does that make sense? So each of these is 80 degrees, which means what I'm looking for is the area of a sector with an angle of 80 degrees. That's what this problem is asking me to find. So I might just go ahead and redraw the picture. This way I don't have to hold all of that in my mind, because really all I need to think about is the circle and that sector. So I'm going to go ahead and put 80 degrees in there, right? That looks more like 90, but that's okay. And I know that my radius is what? If the diameter is 12, radius has to be 6. So that whole circle, right, the area of the circle is pi r squared, or 36 pi. Does that make sense? All right, we got a 36 pi in the whole circle. So how much is just this sector that has an 80 degree angle in the center? Well, we can use a proportion to figure that out. 80 degrees is only part of the way around the entire circle, right? 80 is part of the way around the whole 360. Well, I want the area of that blue sector. And isn't that just part of the area of the entire circle, which is 36 pi? So look at what we have here. We've got a nice proportion. Part over whole equals part over whole. We can cross multiply and solve this. So let's see if I'll take this extra step here. 360a equals 80 times 36 pi, whatever that is. And I divide both sides by 360. So a is going to be equal to 80 times 36 pi over 360. Now that might seem like some big numbers, but really what's 36 divided by 360? That's just 1/10, isn't it? And 80 divided by 10 is 8. So I'm going to go ahead and say this should be 8 pi. I will go ahead and pop it in the calculator just to be sure and show you how to enter this. With something like this, you have to be careful with parentheses. It says 80 times 36 pi. I'm good there, but now I want to divide by 360. So I'm going to divide by, and I'm going to put a parenthesis around that 360. Now in this case, you'd probably get away without it, but if that was 360 times some other number, or if there's more than one term in the denominator, it's very important you have a parenthesis around that. So let's see how I did. Oh, well, I have 25.13. Is that the same as what I got down here? Oh, let's see. I forgot that we're supposed to leave pi in it. So 8 pi, ba-bam, 25.1327. So that's the answer that we're looking for, 8 pi. By the way, I'd like to see a units squared on the end of that. I'm not sure if the regions will penalize you if you have that or not, but I want to see it because this is area and we measure area in square units. All right, so I hope that makes sense. All right, looks like in this one we have a little proof ahead of us. So we have triangle XYZ. They're telling us that XY is congruent to ZY, and now this they haven't marked. YW bisects angle XYZ. All right, so if YW bisects XYZ, what does that tell me about the picture? Angle bisectors divide angles into two congruent angles, right? So that means that that angle and that angle are congruent. Hey, nice. So when I look at this here, I've got a pair of sides, a pair of angles, and don't I have a reflexive right down the center there? So what have I got? Side, angle, side, triangle congruence. Now the question is, how does that help me prove that YWZ is a right angle? Well, if these triangles are congruent, then can we agree that angle 3 and 4 are also going to be congruent? But those are supplementary angles, aren't they? So if they're supplementary and congruent, what do their measures have to be? That's right, they got to be 90. So let's see, how can we lay this proof out? Well, it's going to be pretty straightforward. Since YW bisects angle XYZ, angle 1 is congruent to angle 2. Right? And if you want to be extra careful, you can write because something like, an angle bisector divides an angle into two congruent angles. Okay? Probably could get away without it though, but let's be careful. Also, of course, we were given that, XY congruent to YZ. That was given. And YW is congruent to YW by reflexive. Therefore, do you guys know those 3 dots for therefore? Right, that's a handy little symbol. It means therefore, like I'm going to conclude something from this. Triangle XYW is congruent to triangle. Now you got to make sure these match, right? XYW matches up with ZYW by side, angle, side, triangle congruence. Right? There's our side, angle, side. So angle 3 is congruent to angle 4 by CPCTC. Right? Corresponding parts of congruent triangles are congruent. But wait a second, angle 3 and 4 form a line. So we can finish this by saying something like this. Since angle 3 and angle 4 are a linear pair and are also congruent, they must be 90 degrees or right angles. And that is what they asked us to prove, so I'll go ahead and put a proof box there. If you're not familiar with the proof box, this is the cool way to end a proof when you're a mathematician. It's sort of like saying, there you go, like that's what you asked me to prove, done. Alright, so there you go, relatively straightforward proof from the Common Core, and I think we've got 1 or 2 more left. So let's see, when I first look at this question, I see words, words, words. So I go into what I call what's important mode. Most of this I probably don't need to know. I'm going to look for the important things. Trees are cut down and stripped of their branches are approximately cylindrical. That sounds important. They want me to think about cylinders here. A timber company specializes in a certain type of tree that has a typical diameter of 50 centimeters. That sounds important, diameter of 50 centimeters, and a typical height of about 10 meters. Okay, so let's stop right there for a second. It looks like in this problem we're going to be thinking about mathematized trees, right? So trees that are not really trees, but just cylinders. And these cylinders have a diameter of 50. Now I really don't care about the diameter of a cylinder, I care about the radius. So if the diameter is 50, what's my radius going to be? Just 25. And a typical height of about 10 meters. Oh, I see another problem already. So that's 10 meters, and this is 25 centimeters. Oh, they are really trying to mess with us here. We cannot work in centimeters and meters. Easiest thing to do would be turn the bigger unit into the little one. Do you guys know how many centimeters are in a meter? Cent is a clue. Century. 100. Every 100 centimeters gets you a meter. So if I've got 10 meters, that's 10 times 100 centimeters, right? So 10 times 100 centimeters, 1,000 centimeters, right? And that's the number we got to work with since we're in centimeters down here. So I'll just kind of like put a little red box around that one so I don't accidentally use that. All right, let's go back to the problem here. We're still decoding. The density of the wood is 380 kilograms. So they're asking me to figure out the minimum number of whole trees that must be sold to raise at least $50,000. Well, that begs a question. If I want to know how many trees I need to make $50,000, I need to know what's a tree worth. Does that make sense? Right, if I don't know what's a tree worth, then how can I tell you how many trees? Maybe a tree is worth $50,000. I only need one. Maybe it's worth $1 and I need 50,000. Probably somewhere in between. So to figure out what a tree is worth, we're going to need the volume of this tree. Now, a cylinder is what I like to call a stackable object. That means you start with a shape, in this case a circle, and you just stack circles on top of circles until you get to the height you want. And all stackable objects have the same volume formula. It's the area of the base, which we call big B base, that's B with a capital B, times the height. Well, in this case, the area of a circle is pi r squared, and that's why if you look in your reference table, you'll see the volume of a cylinder is pi r squared h. So we can go ahead and just plug into this. Pi times the radius squared, so that's pi times 25 squared times the height. Now notice here we're working in centimeters, right? So 1,000, sorry, lost my train of thought for a second there. So what is our volume? That one I'm going to probably go to my calculator for. I guess I could square 25, but I don't want to. I'm nervous to try it on camera. So, I should show you what I'm doing, I apologize. So the way I'm going to enter this is just 25 squared. I'm going to type that first, times that by 1,000, and then I'll go ahead and multiply that by pi. So I get a pretty big number. Now watch, I'm going to store that as x, that same feature from before. So if I need that number again, I'll have it. So I'm going to say my volume is approximately 1963495.408. Now hang on a second. What are my units? Something cubed, but what? Centimeters. This is centimeters cubed. And I think that's going to be really important in just a minute, because notice the next part of the problem. Now I know the volume, I need to know how much I can get for this thing. Well, it says that, let's see, the wood is 380 kilograms per cubic meter. Yikes, I have centimeters cubed, not meters cubed. Now here's where you got to be a little bit careful. Think about a 1 meter by 1 meter box. Well, cube if you like, okay? So if that's a 1 by 1 by 1 meter, I'll put meters next to all those so there's no confusion. That's 1 cubic meter, correct? But hold on a second. If we're working in centimeters, 1 meter is 100 centimeters. So this is a 100 centimeter by 100 centimeter by 100 centimeter box, isn't it? Yeah. So what is 100 times 100 times 100? Well, I'll go to the calculator again just so I don't make a mistake there. I'll cube 100 and I get a pretty big number. So what does that mean? That tells me that 1 cubic meter is equal to, let's see, that's 1, 2, 3, 4, 5, 6, 1 million cubic centimeters. Wow, that's going to make that a much smaller number, isn't it? So hold on a second. Remember before I had that number saved as x, that's my volume. So I'm just going to divide that by 1 million. Oh, look at that. So it turns out a tree is only about 1.9634 cubic meters. Do you see what happened there? By the way, I'm going to go ahead and store that as my new x, because I might want that number again in the near future, right? So this is cubic centimeters. I turn this into cubic meters. Now, at this point, I'm realizing that in the early part of the problem, when I converted from meters to centimeters, it might have been easier to convert from centimeters to meters. So just to show you what that would look like briefly, if you had the original cylinder and you wanted to work with meters, then it would be a 10 meter tall by, well, 25 centimeters is only a quarter of 100, right? So this is 0.25 meters. And if we go ahead and apply volume equals pi r squared h to that, then let's see what we get. So pi, let's do the r squared first, so 0.25 squared, right, times pi, times h, which is 10 in this case, times 10, and oh, look at that, 1.9634, the very same thing I already have in my calculator for x. So that might have been a little bit simpler in hindsight, but I like that we had this opportunity to talk about how a cubic meter compares to a cubic centimeter. Either way, we're ready to keep moving on with the problem here. So what's a tree worth? I still don't know. I know that a tree is about 1.9634 cubic meters, but what's it worth? Well, let's see. The density of the wood is 380 kilograms per cubic meter. So what's the weight of a tree? Well, if it's 380 kilograms per cubic meter, that means that the weight is about 380 times 1.9634, etc. cubic meters, right? That means each tree weighs about, here I'm going to go back to my calculator, 380 times, remember I put that number in for x? You see how this can save you a lot of time? So I store that as x, and I've got about 746.128. I'm going to store that as x now in case I need that number again. And what is my units? Well, this is a weight. This is kilograms now, right? So 746 kilograms per tree. That sounds pretty heavy. I think a kilogram is something along the lines of 2.2 pounds, but I'm not sure. These things are pretty heavy, which makes sense. They are trees after all. Do I know how much a tree is worth? Not yet. I'm still working here. I know how much a tree weighs, and I know that the wood can be sold at a rate of $4.75 per kilogram. So what's a tree worth? Well, a tree is worth $4.75 times however much it weighs in kilograms, which is about 746.128. Wow, we are really having to work for this one. So once again, I'll pull my calculator out here. Remember, I saved that number, so I could just hit times, I have it, but I could do 4.75 times x. And I get 3,544. Okay, so worth about $3,544. And now this time I'm going to round. Why? Can I have $0.109212? No. So I'm going to round this to 0.11 because that would be 11 cents, right? And since we're talking dollars now, that's the only thing that really makes sense. See what I did there? Okay. So if that's one tree, we want to raise 50,000. All right, so the end of this is going to be very easy. If we want 50,000, and every time we get one tree, we get that on average, we just need to divide those two numbers. 3,544.11. And what do we get? Well, 50,000 divided by 3,544.11, 14.109. 14.10, let's say 8 trees. Okay, so what is the answer to this question? What is the minimum number of whole trees that must be sold to raise at least $50,000? The answer is 15 trees. Right? Can't get 1.108 tree. I mean, I guess you can, but they said we couldn't, right? So whole number of trees. So I'm just going to move this a little bit so we can just kind of reflect on everything that went on here, because there was a lot. We first had to figure out that trees are cylinders. We had to convert from the diameter to the radius. Get the volume of the tree. We could do this one of two ways. We're going to get the same number either way, but we're going to have to do some unit conversion no matter how we do it. If you end up converting in cubic units or square units, be careful that you pay attention to the fact that it's a cube or a square. It's going to affect the conversion. Volume, once we had that, we use that to figure out how much these things weigh, right? 380 kilograms per cubic meter. So from cubic meters, multiply that by kilograms, we get weight. Now that we know how much they weigh, we can figure out what they're worth. 475 per kilogram, so 475 per kilogram. That's a tree. 50,000 divided by one tree. We need 15 trees. I hope you enjoyed that one. There was a whole lot of stuff going on there. Hope that makes sense. So it looks like we've finally come to the end of this video. This is the last question we're going to take a look at. And it looks like it's going to be a proof. It says that D is the image of A after reflection over CH. So D is the image of A after reflection of CH. Now that tells me a couple of things. One thing it tells me is that CH is the perpendicular bisector of AD. Right? Remember, a line reflection, the line of reflection, is the perpendicular bisector of the pre-image and the image. CH is the perpendicular bisector of BCE. Okay, great. So now I know BCE is also perpendicularly bisected here, which means that B is going to map onto E if I reflect, right? Triangle ABC and DEC are drawn. Yes, they are. Prove that they're congruent. Okay, well, let's see. So if we have a perpendicular bisector, then that's going to tell me a couple of things. Obviously, C is the midpoint, so BC and CE are congruent. Let's start there. Since CH is perpendicular bisector of BE, C is the midpoint of BE, and BC is congruent to CE. Alright, so we got a pair of sides there. Great. What else do I need to make triangles congruent? Well, some more sides would be great, or some angles. Let's see. So what can we do here? We know that these are also the image after reflection. So CH is the perpendicular bisector of that. Can we use that to help us here? Let's think. Okay, sure. So let's see. So that means, right, that therefore, this is another way to say therefore, a double arrow, B and E, right? So I'll say E is the image of B after a reflection over CH, right? So since this is a perpendicular bisector, and the definition of a line reflection is that the line of reflection is the perpendicular bisector between the pre-image and the image, then I know that B is and E maps to E, and we already were told that A maps to D. So hold on a second. So E is the image of B after reflection over CH, and we already know D is the image of A under the same reflection. Well, okay, that's actually pretty good. If we know that B maps to E, and we know that A maps to D under the same line reflection, well, what do you know about line reflections? Do they affect distance? No. Do they affect angles? No. There are isometries, congruence transformations. So that means that this distance, AB, and this distance, DE, have to be the same, right? They were the same before the transformation. Well, whatever it was before the transformation, it has to still be the same length after. Therefore, right, I can say AB is congruent to DE because distance is unaffected by line reflection. So now I've got one pair of sides there, I've got another pair of sides there, and I'm just going to go ahead and finish with the very same argument, right? So AC also, I guess I'm going to have to show that C, okay, so hold on. So I want to make the argument that this is side congruent. So what I'm going to do is say C isn't going to move under the reflection. Since C doesn't move under the line reflection, whoops, sorry, having trouble making an R there. That means that AC is also congruent to CD because distances are unaffected. by a line reflection, which means I now have AC congruent to CD, I have AB congruent to DE, and I have, way up here, BC congruent to CE. So, therefore, right, triangle ABC is congruent to triangle DEC by side, side, side triangle congruence. Proof box, we are done. Now, there's a couple other ways you could have finished that proof. Once establishing that these sides were congruent, you could also go after angles B and E, right? Since you would still need to say that angle C doesn't change under the line reflection, but then you can say, since ABC and CED, right, A is the image of D, or D is the image of A, E is the image of B, and C is the image of itself, then that angle B is going to be unaffected by the line reflection, and B will map directly to E. Then you'd have a side angle side triangle congruence. Doesn't matter how you prove it, as long as you prove it. So I think that's it for this video. I hope you enjoyed it. I hope it helps you out. If you like the video, please like it below and leave a comment, subscribe, and if you have any questions, feel free to send me an email. I'll put my email address in the description. Good luck on the exam.